Hello to everyone. Thank you for attending this event. We're ready to start. Today's webinar is going to be focusing on the experience design and analysis of a shoring system for the 2nd and Broadway station in Los Angeles for the regional connector. We have two presenters, Mr. Piruz Barar, who's a structural engineer and a shoring expert from PBNA with a lot of experience, and Mr. Babak Mamakani, a project manager for PBNA Inc. And they're going to be presenting their work with the DeepEX software that they've done together with their experience from such a massive project. So with that, I'd like to welcome Piruz to start the presentation.
Good morning, good morning or good afternoon, everyone. This is Piruz Barar, and we are going to be presenting this program. And also, Mr. Babak Mavagani will join me later on to, he's the project engineer manager for this project, and we'll describe some of the issues here involved with this project. We're going to have an introduction in terms of introducing PBNA. Then we go through the project. There are two projects actually in Los Angeles. One is called RCC, Regional Connector, Regional Corridor Connector, and also West Side Subway extension, which is called the Purple Line. We're going to some show photos, but we are going to concentrate on 2nd and Broadway station because it was a much more, probably the most complicated of all the stations for which we were the design engineer for the shoring support of the excavation. And then we go from some conclusions, and then we go to ask if anyone has any questions. We would be more than glad to respond. Just to start with, PBNA, we are the structural engineers, but we have been for 35 years. We have done work for earth retentions, deep foundation, slope stability, and shoring and underpinning work. This is a project in 405 widening that we did in Los Angeles, and also we have done. I want to claim that we have from the PBNA is the first designed the first soil layer water in the United States, August of 1983, and we do a lot of soil netting. This is a job in UCSD project, and this is all soil netting. And this is the Boyle Station, and Boyle Station is part of the Gold Line. It's the same line that we are going to be extending, and the issue with these jobs is that they are very complicated because they're underneath live streets. Excavation is done underneath the existing live streets, and so it takes a certain amount of expertise to do that, and there are a lot of familiarity with the methods of construction, and I go through that again. The job that we are concentrating on today is called Regional Connector. This green line in here, and we are responsible. The dotted green lines are tunnels. We are responsible for designing the shoring for 2nd and Hope and 2nd and Broadway. And then on the other line, sorry. The other line is underneath Wilshire Boulevard, and starts. Let me see if I can drag this over here. It starts at the west side. This is the end of the west side line, a western line, and then this is Wilshire Boulevard. It starts underneath the Wilshire Boulevard, and this is Wilshire Station, Wilshire and La Brea, Wilshire and Fairfax, and Wilshire and La Cienega. This is a retrieval shop. The plan is to bring the TBM machine, drop it down in La Brea, and then bring it and do the tunnel to western, and then pick it up and bring it, put it on a truck and bring it back here, drop it here, and then do the rest. And so our mission was to two stations in RCC, Second and Hope, Second and Broadway, and 3 stations in Wilshire and La Brea, Wilshire and Fairfax, Wilshire and La Cienega, and also western retrieval shaft, which was very complicated because it's where it connects to the western line, and fairly complicated job. Now here is Second and Hope. This is 100-foot excavation. This is where the tunnel head, hammerhead is, and there's a utility. Of course, these are all underneath the streets, and utilities is a major issue. There's a utility bridge that goes over the project. This is another angle. This picture on the right is taken from the other end of the station. In other words, this is a station about 500 linear foot long, and this is the other end of it. And this is all, they're pouring the mat slab for to receive the TBM machine at this stage. This is Broadway Station, and this is LA Times building, and this line in here is 2nd Street, live 2nd Street, and there's going to be this is the entrance to the station. This is 80-foot excavation here, and this is almost like a trestle that goes across, and of course there is going to be a commercial building built over the station, over the metro station. So this is that I guess they sold the rights of the commercial rights. This is the underpinning of the LA Times building, and Babak is going to explain to you that part of the LA Times building was extruding into the excavation, and we used a very complicated ground anchor and tieback systems for this scheme. Here, Babak will explain that. Here's the excavated, semi-excavated. There's another 20 feet to go of La Brea, Wilshire and La Brea. This is live Wilshire Boulevard, and all the utilities are hanging from that were there are hanging from the beams. Now, for that specifics, I'm going to turn it over to Dr. Mamagani, and he will explain the design criteria and specifics of the project.
Hi, everyone. Thank you, Mr. Cruz. My name is Babak. I'm the project manager of this project, and I'm going to talk about more in detail about Second and Broadway Station. As you can see, the Second and Broadway Station is part of the RCC and required cut and cover excavation of 500 feet long by almost 100 feet deep underneath 2nd Street. At the bottom, you can see the general layout of the project. We have used a combination of tiebacks and struts in the project. And where we have the LA Times building, we use the special underpinning system to support the footing. And on the right-hand side, you can see the general section of the station, and here you can see the utility, which was originally concrete and was replaced by a hobus pipe and was supported by the deck beam at the top. And the deck beam was kind of a part of the support system of the SOE system. And these two are the picture of the Google picture of the station. Here you can see this is the LA Times building, and on the left side you can see the parking garage, which is right next to the station. Part of the LA Times building, as Mr. Bruce said, was protruded into the excavation, so we needed to support that. And on the right-hand side, you can see the LA Times building, which is almost like a 10-story building next to the station. In terms of stratigraphy, the station consisted of a mainly Fernando Formation, which was siltstone or clay stone, and the top part was like 7 or 8 feet of fill and 7 or 8 feet to 8 feet of alluvium. And at the bottom, you can see the soil properties that we came up with the other geotechnical engineers for analysis purpose. And on the right-hand side, you can see the stratigraphy of the station. Here at the bottom, you can see the station, 2nd and Broadway station. The whole red layer is the Fernando Formation, and then here in the middle is the alluvium, and the top is the fill. In terms of design criteria, we had many criteria to make sure that the SOE was designed appropriately. These are actually was by Metro. The Metro asked us to design the SOE system for 24H here, where we have the restraint system. And there was a criteria saying that if the excavation is greater than 35% within the Fernando, we have to use 24, otherwise we have to use 29H. And this is the trapezoidal pressure that we use for the SOE system design. And this, on the right-hand side, when we had a cantilever system, we use a 30H or 36H based on the existence of the Fernando Formation or alluvium. On the right-hand side, I briefly show the traffic surcharge and the seismic surcharge, as well as how to calculate the building surcharge if it's located within the one-to-one slope of from the bottom of the excavation.
Yeah, I'd like to interrupt, Bob. I can just add something in here, and it's that Metro, over the past 35 years that have been building underground installations, they have developed a design criteria. It's fairly extensive, and we follow that criteria.
Thank you, Mr. Cruz. And also there were some other criteria in terms of how to calculate moment when you are going down in the excavation and when you're coming back up. So according to the criteria, we were allowed to reduce the moment by 20%, and also reduce the moment, as you can see in the second item. We were allowed to use PLS square over 12 instead of PLS square over 8 because of the fixity that the slab provides to the SOE system. And also, there was another criteria about the strut system design, which was asking to limit the axial load to 12 KSI and to limit the slenderness ratio to 120. And the main things, the methods that we used was limit equilibrium and finite element analysis. The main design tool was DeepEX for us. We used DeepEX to design the struts, wailers, and soldier pies and tiebacks. Because the DeepEX provides the feature to have a stage construction and calculate the load at each stage of the construction. Later on, I'll show you the stage construction that we did in DeepEX. And also Plaxis 2D we use sometimes for the deflection analysis.
Let me also add here a couple of things. I'm just sorry I keep interrupting Babak, but there are a lot of the criteria about design of metro, for instance, limitation of the struts having only 12 KSI stress. Basically, seems pretty illogical because you can use high strength steel and so on and so forth. But it has been developed over the years to limit, for instance, this just to limit deformation. That's one issue. The other thing is that we worked very closely with Mr. Dimitrios Kostas, and he actually modified some of the coding of the DeepEX for us to fit into the LA times criteria, LA metro criteria, design criteria.
And here you can see the DeepEX model that we actually generated. As you can see, it's the stage construction within one file only. So first we dig down and then put the first strut, which in this case was the deck beam. And then as we go down, we were able to actually update the apparent earth pressure as we go down. And the program was able to calculate the loads at each stages, which was very critical for us. So as you can see, the load at struts, in this case, changes as we go down and reach the bottom of the excavation to make sure the embedment depth was adequate. In this case, the factor of safety for embedment is 1 because the active and passive pressure was allowable. And then we're able to actually coming back up for the slab and then take out the level D strut and then come back to the concourse level, model it in the DeepEX. And then, as you can see in this stage, I forgot to mention that, for example, in this stage, this is the critical stage to design the soldier beam. And the load on the level C strut, as you can see, is 54 kip per linear feet, which is the highest during the construction. So these were really important for us to know where the loads are going to be maximum and design the SOE accordingly. Because one of the criteria, for example, for tiebacks was that we needed to test the tieback to 1.5 of maximum possible load during all construction stages. And the underpinning, as I said, was one of the most challenges in the challenging thing in the Broadway station. You can see here it was located here at the east side of the project. And here is on the right-hand side, you can see the section through that area. This is the LA Times building footing sitting right next to the station, and the wall footing is actually going inside the station. So we needed to support this two system, make sure the LA Times building will not settle or move during the construction.
This is used to be in the old days. They used to have a pop-out essentially next to a building for receiving material, cargo and so on and so forth. And it's actually underneath the sidewalk. And so this little structure was sticking out of the building perimeter into the excavation, and it definitely was a challenge to not only underpin the whole building, but also to hold out this cantilever.
So this is showing the the front actual view of the underpinning, and to do that, actually to support the building, we came up with the ground anchor system with the actually precast concrete panels. So here at the bottom, you will see what was the process that we followed. We dig actually 3 feet under locally below the foundation and to install the breasting boards to support the soil not to collapse during the excavation, and then go further down to reach 6 feet below the foundation, and then install the precast concrete blocks in the location, then support it with the timber blocks, and then anchor it, and then lock it in the location. So we did that in the process. As you can see, we have numbered all of the blocks. So all of the number ones went first, and then number 2, and then number 3 for the first layer, and then they went down, and then did the same process for the second layer. And then for the rest of them was a hand dug pit. So as they were going down, they were locally excavated, put down the reinforcement cage, and then pour in the concrete. And then after the concrete is cured, they put the tie back and lock the tie back in place. These are some photos of the underpinning. As you can see here, this is the footing which is supported by the underpinning system. These are the boarding breasts that was supporting the soil from collapsing into the excavation area. These are all plates that are connecting all of the concrete panels to each other, so make sure they do not move with respect to each other. So we actually get minimum or insignificant movement.
Yeah, I'd like to add here that the original design called for poured-in-place ground anchor panels, and a lot of credit goes to the contractor RCC that they came up with a precast version of what our design was for basically schedule issues, and also that underneath the building, they use these tunnel techniques as piling. In other words, you just had putting these rebars and grounded rebars to hold up that protrusion into the excavation.
And also, we ran a Plaxis analysis to make sure that the deformation are within the acceptable range. So here is the deformation and the deflection and the stages that we did in Plaxis. And also, as a conclusion, to wrap it up, so as I mentioned during the presentation, the critical stage does not always occur in the final stage of construction. And DeepEX helped us to model the whole construction stages and make sure that we capture the maximum possible load that strut or tieback will be experienced during the construction, and design it accordingly. So, and also we had a very like many inclinometers around the station, and none of the inclinometers showed excessive movement during project. Now the project is all the way down, and they've poured the slab, and they've removed the level D strut, which was the most critical stage for us. And we noticed that the load are almost what we expected to be. And also the sensor that was installed on top of the LA Times building, the tilt sensor, showed very minimal movement. So we were sure that the ground anchor system that we provided actually is doing its job.
I just also wanted to add the contribution of Demetrius and DeepEX, because what happens is that in other shoring design programs, essentially you capture just one stage of the excavation, You know, normally you say, okay, I'm going to go down 40 feet, and here's what happens at that stage. But in projects like this, it's really DeepEX is a very powerful tool because it's stage construction. In other words, you go down and come back up, and then you choose a critical stage.
So with that, I think we are ready to take any questions. So,
Piruz and Babak, thank you very much for your kind words for the work that you've put together for DeepEX, and we're really glad to help with this project and customize the software. I'd like you to emphasize, for those that have not worked in such a big project, what are some of the particular challenges that an engineering firm like yours has in working with such a big, massive project? So what are some of the finer details that one will really need to pay attention to? And let's not only focus on software, but like, let's say 1 to 3 items that will be particularly interesting or somebody needs to pay attention to.
Well, I'd like to answer that. Nobody wants to give a job like this to somebody who hasn't done it before. So the main issue is that you have to have experience in, and somehow what is it, about maybe 20 years ago, I got this project in Pasadena with that was the first job of a cut and cover it was a gold line in Pasadena. So once you get the first job, then you start learning the trade and you go from there. So the challenge here is that utilities are major big challenge because you're working underneath the live street and utilities. There are a lot of utilities in coordination with the design team, and then of course a lot of these excavations are next to very major buildings. Deformation. Shoring is all about deformation. It doesn't. Design is something, but the deformation of the system is another issue. Then the previous experience connections, of course, are very important. A lot of these connections was developed by us in the goal line 20 years ago. That first picture I showed you. So it's experience. Experience has got a lot to do with it, and also being RFIs, and you're being very immaculate with keeping track of the documents and so on and so forth. It's a very challenging job, no question.
Okay. So there's a question. How were the live streets supported? So I guess this goes back to the decking beam, and the decking beams being placed on top of the piles, and then the street being going back live to traffic, correct?
Yes. So what happened? They excavated to install they installed the soldier piles. After that, they excavated down to the bottom of the first level. In this case, is the decking system. And then they install the decking system to on top of the soldier piles and connect them all together. And then once everything is installed, the concrete panels were installed on top of the decking system, and the traffic started to actually open to the public. And then they continued underneath.
Yeah. Let me also add this that originally, many years ago, when LA was building these stations, the format of it is that these pre-stressed precast panels that are 14 foot long by 8 foot wide, and they are pre-stressed, and they're, I think, 8 inches deep, right?
Yes.
So what happens is that you have to go on the street on a weekend, dig trenches. But first you have to put soldier beams in, and then then dig trenches and put in these deck beams, which are, 40 inches, 30 heavy 36 wide flanges at 14 feet on center. Then another we can come back and dig everything out and put these panels on, and then go from the entrance station or some corner of it and start digging digging underneath the street. And of course, once you do that, then there is utilities that are existing. Then you have to hang the utilities from the deck beams, and it's it's not an easy job.
I just want to have that the beauty of this system, that the decking was integrated into the SOE design. So the decking was not only designed to take the live traffic, but also a lateral surcharge of the soil, and also utilities and all of those things that are hanging from the decking system.
Good. So now, Babak, obviously, I think pretty much everyone here that is attending this webinar is younger than Piruz. But as a relatively young engineer, what's your recommendation to younger engineers that are probably watching this webinar? What is your advice and what is your experience? Could you summarize that in under a minute?
Yeah, the advice I have for younger engineers is that engineering really is not all numbers. One thing that somebody told me a long time ago is that you have to know the answer of a problem before you start looking at it. So which all goes back to the point that you have to do you have to have an experience of doing a similar job. We get a job, and pretty much we know what the answer is, and then we do calculations to verify that. So the issue with the younger engineers is that how do you get the first job? And that is once you do the first one, then you just have to build on it. And it takes I've been an engineer for more than 50 years, and it is you just have to gain experience. It's an experience, more than anything else, experience oriented, and you can't become cocky with your experience. You just have to look at the project. Every project has a unique characteristic, and you can't just rely on your experience, and you just have to calculate it. You have to do the analysis, and Mr. Babak is good at that.
So Piruz and Babak, thank you very much for the presentation. Let me see if there's any other questions.
Sure.
Anyone on the chat, please? So there's a question: how were the design pressures developed? And was monitoring conducted to measure loads in the struts? And if so, did the results validate the pressures or indicate they could be lower?
So initially at the Second and Hope station, when we started having the 24H, we developed we conducted a study to see if we can lower that pressure, because if you put more pressure on the system, the more pressure you're going to get in the struts and then all of those things. So we kind of did that analysis and told Metro we can use the 21H, but at the end of the day, when actually they construct the station, put all of these struts in and measured the loads, they were getting almost what we were expecting, 24H in this system. So there was not that much of room to actually reduce that. So that 24H is a kind of a conservative number. But due to the unpredictable loadings and eccentricity of the load and all of those things, 24H for these stations was really good number.
Yeah. Well, and this is another, it goes back to my original comment, was that geotechnical engineering, has got is the same rule applies. The people who write these pressure diagrams are very familiar with it as local stratigraphy, and that so the lateral air pressures are not really an issue here. Because of a lot of these, especially for instance in La Brea and Fairfax stations, these excavations are directly underneath major buildings, and the surcharge of that would be the really predominant design factor. And the very conservative criteria that you limited stresses in the struts by 12 KSI, that helps a lot.
So there's another question if the DeepEX analysis was done using the limit equilibrium method, or if the nonlinear method within DeepEX was used, or FEM. I think I can answer that question. And the basic analysis was done with DeepEX in limit equilibrium for the design of the system. We had done some nonlinear analysis for checking displacements, but the final displacement results for critical sections were conducted with the finite element method. But all the sizing was done with DeepEX in the limit equilibrium method, because in fact the specifications by Metro, and Piruz, correct me if I'm wrong, basically require that the system is designed with the limit equilibrium.
Yes,
yeah, that's correct.
That's correct, yeah.
So we were given all of the criteria, the pressure, all of the things. So we needed a software to actually model everything, all stages with the all pressure that we were given, and actually we use the limit equilibrium for that purpose.
So basically, when we worked with PBNA on this project, we said, okay, we wanted to make the design very efficient, because otherwise, with using the pressures at 24/8 or 29/8, depending on the soil profile you have to use, and the manually specified passive pressures and active pressures below the excavation, it will get quite cumbersome to manually calculate those pressures and then insert them in a structural analysis software or in some other, let's say, not such advanced package that doesn't include all these pressures. So we worked together with PBNA in this and said, okay, it makes sense for us to help, and we always help our clients, and this made the design process much faster. But my conclusion, my summary basically comes out to that, like any software that you use, it's a great tool. There might be recommendations in the software, but at the very end, it comes down to engineering judgment and experience. So, you have a great tool, but you have to always couple that with experience.
Yeah. Well, and also that, Dimitrios, I want to thank you that what happened, there were some very specific requirements by Metro in terms of the passive pressure configuration and so on and so forth that became to you, and you actually did created a specific methodology in DeepEX to use that particular criteria that they have for passive pressures.
So let's see if there's any last questions. We're going to take one last question, please. I'm not seeing anything. So Piruz and Babak, thank you very much for this very interesting presentation. Thank you for using DeepEX and working with our software. It was always a pleasure working with you on this and always interacting. Thanks to everybody for attending. For those of you that have not been able to listen to the presentation because you were not able to connect to the audio, the presentation has been recorded. We're going to be uploading it in the following days on our YouTube channel, and we're going to be emailing you the link so you can share it with other people. Thanks to everyone for attending. Have a good night.
Thank you, everyone.
Okay.